Hello, everybody. Greetings from Anchorage, Alaska. I'm here on business, uh, and I'm exploring and documenting the effects from the November 30th earthquake that happened here. I felt a couple of aftershocks and seen a lot of interesting damage. And so it's been a good time that I've had here, except that it's freezing cold. But that's to be expected in December in Anchorage, Alaska. Anyway, today's lesson is going to focus on the important topic of bearing capacity. Bearing capacity is a understanding and a skill that every single geotechnical engineer should know and understand, and it's something that you're going to be held accountable for when you take the fundamentals of engineering exam on your path to becoming a professional engineer. In a nutshell, bearing capacity is simply the soil's ability to support a vertical load. If you put something on the soil that's too heavy, the soil is going to develop a shear plane, and whatever it is that you put on that soil is going to tip over. Just like this grain silo in this old historic picture, it was too heavy, the soil couldn't support it, and it tipped over. And that's what we're going to talk about today. We want to learn some methods of how we can predict bearing capacity of the soil. But to do that, we need to understand where those prediction methods come from. Now, anytime that I have a foundation and I'm worried about vertical deformations, really all vertical deformations are going to come from one of two sources. It's either going to come from settlement. So you'll remember we've already talked a lot about settlement. I can have elastic settlement, or I could have consolidation settlement. I think it's time to get a new pen for my tablet here. This one doesn't seem to be working very well. And we can also have secondary consolidation settlement. The other method, though, is bearing capacity. And the difference between these two really is that settlement can come from, or settlement can be from a variety of different sources. Settlement can be from elastic behavior of the soil. It can come from void redistribution. So that's things like consolidation settlement, those kinds of things. But the important thing to remember that in either of these cases, that when you're talking about settlement, okay, in reality, the particles don't move relative to each other. I'm trying to write here. Boy, I think this pen is about done. Okay, but when I talk about bearing capacity is and always will be a phenomenon related to shear, which means that the particles do move relative to each other. Oh boy. I'm looking at the tip of my little pen that I use, and it's totally bent in half. Guess I pressed too hard on it or something. Okay. Now, while both of these methods use different mechanisms to cause vertical deformation in our soil, the building won't really notice the difference. All the building knows is that it's moving vertically, and you're going to see very similar evidences and very similar signs that vertical movement is occurring. Maybe the doors won't open or close right, or the windows won't open or close right. You might start to see cracks forming in the side walls, and you might see cracks in the corners of your foundation or your foundation walls. These are all telltale signs that vertical deformation is occurring. But you need to figure out whether it's coming from settlement or whether it's coming from bearing capacity failure. Now, there's two main types of foundations that bearing capacity applies to. We can have what we call shallow foundations. Shallow foundations are any foundation where the bottom of the footing is generally less than about 4 times the width of the footing from the ground surface. So if I have, for instance, a 6-foot wide footing, then as long as the depth of my footing is anything less than 24 feet, then I can consider it a shallow footing. Now, a deep footing or a deep foundation is anything where the bottom of the footing is deeper than 4 times the width of the footing. So I might have driven piles, I might have drilled cast in place piles, I might have caissons. There's lots of different types of deep foundations. I'm not going to talk about the different types of foundations. That's something that we talk about in a later course. It's actually not 542 anymore. They changed the course numbering to 442 so that it will count towards one of your senior design electives. This is a very good course taught by a very good friend of mine, Dr. Kyle Rollins at BYU. I strongly recommend that those of you in my class register for 442 and take it while you're at BYU. Now, when we talk about bearing capacity, let's generalize our footing as just a simple uniform load on the ground surface. And we represent the uniform load with our good old friend little q. And we're going to assume that this is an infinitely long load, so it's a strip load. And our strip load has a width that is equal to b. So here we go. Now there's 2 general types of shear failure that we could see in bearing capacity. Now suppose that I had a really dense sand. What I would tend to see is as the soil began to settle, or as the footing began to settle, I would see an increase in strength, but eventually it would peak out. Oops, I'm not sure why that screen changed. It would peak out and then I would begin to lose strength. Okay? So in other words, it begins to soften as it settles more. This is a phenomenon that we call, let's see if I can get that up. This is called general shear failure. General shear failure. And this occurs when we have dense granular soils. And so the telltale sign of a general shear failure is that we get a rotational failure, that this failure plane extends all the way to the ground surface, and I get to see this nice heaving rotation, this nice big block, and my load will actually spin out. Now, sometimes if the load just goes straight down, I'll also get another shear failure and shear plane that goes all the way to the ground surface on the other side. And so the key to remember is that with a general shear failure, the shear plane goes all the way to the ground surface. And as a geotechnical engineer, my rule of thumb is that if my drained friction angle of my soil is greater than or equal to about 36 degrees, I can safely assume that I'm going to have a general shear mode in my bearing capacity. But suppose I have a loose sand. If I have a loose sand, what's going to happen is as my soil settles, I'm going to slowly see an increase in the amount of bearing capacity until eventually I plunge my load and it's just going to go down and I'm not going to get any more resistance from the soil because I've completely failed it. This is going to produce what we call a punching failure or a local shear failure. They both mean the same thing. The point is, with local shear, I began to develop a shear plane in the soil but the shear planes remain local. They don't extend all the way to the ground surface. So I might get just a little bit of bulging around the footing, but I don't get a shear plane that goes all the way to the ground surface. And the reason that I don't do that is because, one, as the shear plane develops locally, it's actually densifying the soil in these regions. It's causing the soil to get closer together, but it's not necessarily causing them enough to shear. So in other words, there's enough voids in this soil that as these zones of soil are pushing, there's enough void space in the sand and in the soil here that it can accommodate that movement, and it does not develop a shear plane that goes all the way to the ground surface. And then also this geometry of this shear plane here, this is going to change with the settlement. So in other words, as this plane gets pushed down, these zones of failure will kind of shift and move around, but they never actually go all the way up to the ground surface. So the thing you need to remember is I have two types of bearing capacity failures. I have general shear, I have local shear, or also called punching shear. And they each have very different mechanisms. So here's a couple of pictures that I've just pulled off the internet of different types of bearing capacity failures. In each of these pictures you can see the structure itself tends to look totally fine. The only thing that happened is that the structure tipped over and the soil couldn't support it anymore. So how do we predict what the bearing capacity of the soil is going to be? Well, the father of modern-day soil mechanics, Carl Terzaghi, developed the theory of bearing capacity, and the way that he developed it is actually very, very interesting, and I think we can learn some very important stories from it, or very important morals from it. You see, when Carl Terzaghi was developing the theory of bearing capacity, the world was engulfed in the middle of a world war. And Carl Terzaghi, he tried to get his inspiration from multiple sources. And one particular day, he was reading a journal paper, a scientific paper by a German author named Prantl on this theory of armor-piercing ammunition and how bullets could pierce armor. And Terzaghi looked at that and he said, the shape that the metal makes when the bullet pierces the armor looks a lot like the shape that the soil makes when a foundation pierces into it. And so he took and built upon a lot of the theories that Prantl developed for metal, and he applied them to soil. And here's what he came up with. It's really quite fascinating. So here I have my foundation. It's buried at some depth, d sub f, and it has a uniform load of Q sub U. And if we load this foundation up, what we're going to see happening, a couple of things. First of all, I have an elastic zone. This is a zone directly beneath my footing. And it develops in the shape of a wedge, or like a pyramid. And as the footing goes down, this soil gets trapped and it actually becomes kind of like a snow plow or a blade and becomes like part of the footing itself and helps drive the soil beneath it out of the way. The next zone is what Terzaghi called the Prantl zone. And he called this the Prantl zone in honor of the researcher Prantl, whose theory he used to develop this methodology, which I think is really cool. I mean, he could have called it the Terzaghi zone if he wanted to, but Terzaghi wasn't like that. He wanted to give credit where credit was due. But in the Prantl zone, the shear plane develops and it begins to seek the path of least resistance. So the shear plane isn't necessarily going to just keep going down into the soil. No, because if it did that, it would require more and more resistance. Rather than that, the shear plane is going to turn around and start trying to head its way back up to the ground surface, because that is the path of least resistance for our shear plane. The final zone is what he called the Rankine passive zone, and this is a zone highlighted here, and it's on the other side of my footing as well. And this is a zone where the Prandtl zone is literally just, boy, that is the ugliest arrow I've ever drawn. The Prandtl zone is just pushing on this Rankine passive zone. And so this Rankine passive zone is in compression, and it's just sliding up this failure plane towards the ground surface. So it's just like a Rankine passive failure. So we have these three zones. We have the elastic zone, the Prandtl zone, and the Rankine passive zone, according to Carl Terzaghi's theory. So now all we need to do is develop some free body diagrams. And so taking the elastic zone, that's exactly what he did. He drew some free body diagrams and said, okay, where's the weight coming from the footing? What's the weight of the soil mass itself? What about the resistances coming along the sides? They come in the form of friction, and they also come in the form of just resistance, compressional resistance from the soil. So according to Terzaghi, we can divide up the bearing capacity resistance into three components. The first component is friction along the sides of our elastic zone. And because friction is a function of the effective stress, and effective stress increases with depth, what we tend to see is that the friction along this failure plane increases with depth. And in order to get the correct direction, it's not a horizontal, it's not a lateral earth pressure, and it's not a vertical earth pressure. We have a new K that we use to compute the earth pressure along this angle here of our elastic zone beneath our footing. So we call that, or we compute that with K gamma. The rest of this should look familiar though. 1/2 gamma h squared. That's just computing the area of our pressure distribution that's acting along that failure wedge. That's really what we're trying to get. Okay, the second component of bearing capacity could be cohesion in the soil along that elastic zone. So again, we know that along the sides of this elastic zone, as it's being pushed down into the soil, that there's going to be cohesion along those sides. And because there's cohesion, and we know that cohesion is independent of the effective stress, it's going to be a uniform pressure along that failure plane. So to compute the area from that pressure, it's just going to be cohesion times the height, or the depth of our elastic zone, and we're going to multiply it by a different earth pressure coefficient, in this case of C. Now the third component of Terzaghi's bearing capacity theory is just the weight from the surcharge itself. So as I have this soil that's out here on the sides of my elastic zone, and this soil is trying to push up, or this elastic wedge is trying to push up the soil out of the way. This soil that is, we're calling it the surcharge, is pushing down, and it's trying to resist the rotation of the Prandtl zone and the Rankine passive zone. So because of that, that weight of the surcharge also provides a resistance to the downward movement of the elastic zone. And that is also going to be a constant stress with depth. And we compute that area as Q. Q meaning Q is simply the unit weight of the surcharge times the depth of the surcharge. So, or in other words, that's often depth of the footing itself. Depth of the footing. That's how we compute the surcharge. Okay, and we're going to have an earth pressure coefficient for that one too. That's going to be K sub Q. That's going to be different from K sub gamma from friction and K sub C for cohesion. So if we combine all those resistances together, we get our resulting resistance along our elastic zone of our wedge, which is P sub P. And so, according to Carl Terzaghi, he said that the ultimate resistance or the ultimate bearing capacity that a strip footing could achieve in any granular or non-granular cohesive soil is going to be equal to this equation right here, where now we have the three components, of course. We have this first term corresponds to the friction, the second term corresponds to the cohesion, and the third term corresponds to the surcharge. These are the three contributions, or the three methods, or the three components, I should say, that contribute to bearing capacity resistance in the soil: friction, cohesion, and surcharge. So this theory from Terzaghi was groundbreaking. It was actually amazing, and researchers have been working and adding and building upon it ever since. Terzaghi's original work dealt with infinite strip footings, but other researchers have developed relationships for square footings and for circular footings. They've developed relationships for bearing capacity of stiff soils over soft soils and soft soils over stiff soils. And so you have multi-layer solutions, and there's all sorts of stuff out there. These are just very simple equations for a uniform soil layer beneath different footing shapes. So the only thing that's different about these equations is the shape of the footing, or the shape of the load. Now, I want to focus on these Q's right here, okay? Notice that this Q in the second term refers to the pressure of the soil above the base of the footing. This is the surcharge, okay? This is the pressure from the surcharge. So when I say that Q equals gamma times the depth of the footing, that gamma is the unit weight of the soil above the footing. But this gamma term right here in the third term, this gamma right here, is the friction term. And remember that friction comes along the sides of the elastic zone. So that is below or beneath the footing. So this gamma right here is below, for the soils below the footing. This gamma, or the gamma that you use to compute that surcharge, is for the unit weight of the soil above the footing, up in the surcharge on top. So make sure that you use the right unit weights, okay? Now, we used the 8th edition of Doss's Principles of Foundations textbook, and in table 16.1 of that textbook, you can find your different equations. Now, I guess in the previous slide I called them K, now I'm calling them N. That's what most researchers use today, not to confuse them with lateral earth pressures. Same thing. I have N sub C, N sub Q, N sub gamma. These are just the earth pressure coefficients to compute bearing capacity. Table 16.1 in the Doss textbook will give you these factors for the case of general shear failure, something that you'd see in soils with a friction angle greater than about 36 degrees. The problem is that in the 8th edition of Doss's textbook, he removed the bearing capacity factors for local shear failure, which is disappointing to me because it's really important. We need to be able to have those factors if we have a loose soil or a soil that might have a friction angle less than 36 degrees. So if you have a soil with a friction angle less than 36 degrees, here you go. I'm just going to give these values back to you. These aren't in your Doss textbook, but I'm giving them to you here. So if you're doing bearing capacity design and you have the case of local shear failure, use these bearing capacity factors instead. Another approach that you can take is rather than trying to decide, should I assume local shear or should I assume general shear? Some researchers, very famous researchers, particularly Peck, this is the famous Ralph Peck. Whoops, I went ahead here. Ralph Peck and Hansen and Thornburn said, well, why don't we just envelope the local shear solution with the general shear solution and pick the lower of the two, and then we'll be good. And so when they developed then these combined equations, they put everything into one single chart. So now, depending on what your friction angle is of your uniform soil, or if you prefer, maybe you can also correlate it with field standard penetration test blow count, whatever you prefer in that sense, or up here, I'm sorry, is relative density. You can also use that. You can come to this chart and you can get your N gamma or your NQ values. Now you might ask yourself, wait a sec, where's N sub C? I don't see an N sub C plot on here. Well, that's because this plot is for cohesionless soils. We're assuming that C, cohesion, is equal to 0. Therefore, there is no cohesion or need for cohesion in these charts. So let's do an example problem with a cohesionless soil. I have an ultimate Q, or I want to find the ultimate bearing resistance and the ultimate load for an 8-foot by 8-foot square spread footing in the following soil profile. The bottom of my footing is 2 feet below the ground surface, and I see that I have a upper clay layer of unit weight of 110 pounds per square foot, or cubic foot, excuse me, and then my footing is resting on sand with unit weight of 115 pounds per cubic foot and a friction angle of 34 degrees. So my very first question to you is, should I assume that with this sand layer, should I assume a local shear failure or should I assume a general shear failure? If you said local shear failure, then you are absolutely correct. It's because the friction angle is less than about 36 degrees, so we're going to assume local shear. Now, at this point, it becomes pretty easy. What we're going to do is we're going to go ahead and compute a couple of things that we're going to need for our bearing capacity equation. First, let's compute the surcharge from this clay that is our overburden, basically in the soil above the bottom of our footing. So that's going to equal the unit weight of the clay times the depth of the footing, which we're going to say is 110 pounds per cubic foot because that was given to us. And the depth of the footing is 2 feet because that was also given to us. So that means that my surcharge is 220 pounds per square foot. The width of my footing is also given to us. That's B, and that's going to be equal to 8 feet. And the cohesion in my soil below my footing that my bearing capacity, or I'm sorry, that's providing my bearing capacity resistance, or that my footing is sitting in, that's going to be equal to 0 because remember, this is cohesionless soil. So for a friction angle of 34 degrees in local shear, all I have to do is go back to the earlier slide, the table that I gave you, and look up the N values for a friction angle of 34 degrees. You're welcome to pause the video or go back in the video and have a look at those tables if you want, but I'll just tell you what you'd get if you were to go and pull out those values. For NQ, I get 11.67. For N sub C, I get 23.72. And for N gamma, I get 7.22. Okay, so now I just have to pick the right equation for the right shape of footing I have. I have a square footing. I don't have a strip footing. I don't have a circular footing. I have a square footing. So I want to make sure I use the right equation for a square. So this is it. So now, once I have it, all I have to do is start plugging in all my numbers. And that's exactly what I do in this portion of the equation right here, and I get a value of 5,224 pounds per square foot. That's my ultimate bearing capacity in this bearing layer of sand when my footing is buried at a depth of 2 feet on top of it. So that gives me little q ultimate. But now I want the ultimate load, not the ultimate pressure. So all I have to do then is multiply my pressure by the area, the area that I'm dealing with. So the area that I'm dealing with is an 8 foot by 8 foot square footing, multiply pressure by area, and I get a force. And the ultimate load that I can place on that area is 334,359 pounds. Okay, so a very simple example, but this is a good example of the type of problem you might encounter on the FE exam. This is a useful chart. If you don't know the friction angle, but all you have is standard penetration testing, you can correlate the standard penetration testing to drain friction angle if you're dealing with sands or sand-like soils. Now, a couple of more things we need to consider. You have to remember that bearing capacity, folks, is an effective stress phenomenon, which means that we have to account for pore pressures. All of these stresses that we're dealing with have to be effective stresses. So that means when we deal with unit weights, like the unit weight with my surcharge or the unit weight with my friction below the bottom of my footing, that I have to use the what I'm going to call the buoyant unit weight. And remember, that's going to be the buoyant unit weight is gamma prime, and that accounts for also the unit weight of water. Now, I have 3 different cases of where my water table can be. What if, in case 1, my water table is above the bottom of my footing, but it's not all the way to the ground surface yet? So it's somewhere beneath the ground surface and the bottom of my water. Well, if in this particular case, if the water table did happen to be at the ground surface, it would be easy. Gamma 1 and my surcharge would just be the buoyant unit weight. So gamma saturated minus gamma water. And gamma 2 would be the unit weight, or the buoyant unit weight of the soil beneath the bottom of my footing. So gamma saturated minus gamma water beneath the bottom of my footing. Now, what if the water table is somewhere beneath the ground surface but above the bottom of my footing? Well, then for gamma 1, for the surcharge, I have to do a weighted average, because I have this portion here that's gamma moist, and then I have this portion here that is gamma buoyant. And so I have to do this unit, or I should say this weighted average. And that's how I can compute that for gamma 1 for use in this equation. Case number 2 is pretty simple. Case number 2 is, what if the water is right at the level of my footing, which actually happens more often than you might realize. Now, if this is the case, then it's pretty simple. Gamma 1 for surcharge, I'm just going to use the moist unit weight. So up here, it's just gamma moist. Now down here for gamma 2 in my friction zone below the bottom of my footing, it's saturated, so I'm just going to use the buoyant unit weight. Pretty simple. Okay, case number 3, what if my water table is below the bottom of my footing? If that's the case, well, if the water table falls somewhere between the bottom of my footing and a distance of I'm going to say B below the bottom of my footing. If the water table is somewhere in that distance, then I have to do another weighted average, but this time for my unit weight below the bottom of my footing. But what if the water table falls deeper than a distance of B below the bottom of my footing. So the water table is well below the bottom of my footing. Well, if that's the case, then I'm just going to use gamma moist, or the moist unit weight, for all of my unit weights. Okay, we're nearing the end here, the things we want to talk about. Let's go ahead and talk about or introduce you to the idea of factors of safety with bearing capacity. Bearing capacity is something that we tend to have a lot of uncertainty with. And it totally makes sense, right? Because there's so much uncertainty whenever we deal with what's beneath the ground, because we can't see it. And we can only sample the soil in select locations, here or there, but we can't sample or know what all of the soil is. So we often apply heavy doses of conservatism when we deal with bearing capacity in the form of a factor of safety. Now, when we deal with bearing capacity, we compute what is called the allowable bearing capacity. And this isn't the ultimate bearing capacity. It's what we're going to allow the engineer to actually use in design. And all it is the ultimate bearing capacity divided by some factor of safety. So what factor of safeties do we typically use when we compute our allowables? Well, because we're trying to be pretty conservative as geotechnical engineers, it's not uncommon to use factors of safeties between 2.5 to 3. Now that seems like a lot, but you have to remember that there's a lot of uncertainty. So we want to make sure to capture that uncertainty by having a very high factor of safety. So we're basically going to cut our ultimate bearing capacity by a factor of 2.5 or 3, just to be safe. And then that's what we're going to allow the engineer to use for design. Now, engineers over the last 15 years or so have really been moving away from this allowable stress design, and they're moving towards load resistance factor design, or LRFD. And they've asked geotechnical engineers to come along for the ride. And that's okay, because LRFD is absolutely fine. There's a lot of really good principles associated with it. So if that's the case, rather than having a factor of safety, this time we're going to just multiply our ultimate bearing capacity by some resistance factor, phi. This isn't friction angle, folks. This is a different phi. It's the resistance factor from LRFD design. And we're going to multiply it by a factor of anything between 0.4 to 0.7. So, which actually corresponds, if you do the math, to a factor of safety of 2.5 to 3. So, at the end of the day, it's the exact same thing. We're just using different annotations to show that. So that's the end of my lesson, folks. I appreciate your attention here. Now I'm going to upload a part 2 of the bearing capacity lessons here in the next couple of days. And in that we're going to get into bearing capacity design charts. And we're also going to get into net bearing capacity versus gross bearing capacity. And so it's going to be a really good lesson. I'll look forward to seeing you then. Make sure that you look at the description, by the way, down in the description box, so that you can get the critical questions that you may want to answer from this lesson, because those are going to be what you're held accountable for on the final exam. With that being said, I want to thank you for your attention and hope you have a great rest of your day.